wasting much time, start looking at it. Right? At the end, we will be looking at, those of you are writing on my screen, please stop that. At the end, we will be having these topics under discussion. We need to know what a matrix is, what is a vector. We establish the relationship between a vector and a matrix. We also want to know the types of matrices. We look at the matrix operations. We also need to consider how we can transpose matrices. Also find the inverse of matrices in terms of the determinant, the minors, the cofactors, the adjoint. And lastly, we will end with looking at linear equations. At the end of the session, these are going to be the learning outcomes, right? The key thing is that we also need to know the applications of matrices, right? And then one of the things that we have to know is that if we are given a set of linear equations, how can we be able to convert it into a matrix and then solve for the unknowns in the matrix equation from AX equals to B? And also, if you're also given a matrix, how can we also convert it into the matrix of coefficients together with unknown variables as well as the known variables B? How can we be able to also convert that one to a linear system of equations? That will also be looked at as well. So then when we talk of a matrix, what comes in mind? Basically, a matrix is referring to a set or a group of numbers which is basically arranged in a square or a rectangular form, normally in an array form, enclosed using two brackets. Basically that. So you can look at this example and you can see that this is basically a rectangular form of a matrix. This is a square form of a matrix. This is also another square form of a matrix. And then what is inside is what we refer to are the elements or basically the numbers. So that's what happens when we are dealing with these kinds of matrices. Okay, you want me to amplify my voice? Let me see. All right, so we want to be able to also look at some advantages when you are dealing with what the matrix. But before that, the key difference between a vector and a matrix is that the relationship between the two is that a vector is a single row matrix or a single column matrix. That's what a vector is. So this can be a very example of what a row matrix, which is basically a vector. If I also have it transposed in the column form, then we can also refer to it as what a vector. So a vector basically is a type of what a row matrix or a column matrix. That is what basically a vector is. So there are two key advantages when you are trying to understand matrix algebra in mathematics. Basically, it reduces the complicated system of equations to simple expressions. So the last thing we might have to look at is the linear system of equations, right? Back in your senior high, I'm sure you came across what we refer to as simultaneous equations, whereby you were given like some three equations, for example, with three unknowns, x, y, z, and then you were asked to find x. So what you were doing was you were dealing with a substitution approach. You can make one of the unknown variables a subject and you substitute it in the two equations and then you solve for x and y. So that's what was really happening back in the senior high. But in here, we're not going to be doing that. We're going to actually look at it in a different way. We're going to look at it in a different way. Then at the end, we want to be able to see how this is going to dance down with you. The other one too is adaptable to systematic method of mathematical treatment and then well suited to computers as well. So if you have a set of images, which we'll be looking at probably the applications as we move on, you realize that matrices play key role when you have an image and you want to convert it into a form of zeros and ones, and that's normally is represented as a matrix. And we can actually be able to go through, and then even if you are doing compression of that image or you want to do decompression, matrices play key role when we are doing certain things like that. So this is the elements in the matrix, the numbers normally, right? We can also have variables as well. So it's not always the case when we deal with variables. But last week we came across the fact that if you're having a variable, which basically is like a parameter in a function, when we call that particular function, please mute. When we call that particular function, we can easily now be able to have a fair idea of an actual numeric value assigned to it, and that becomes the argument. So you can refer to your lecture notes on functions as you looked at last week, right? The other one too has to do with what some properties we need to know. One thing I have to also tell you is that we normally have to talk about a matrix based on the number of rows and the number of columns, which we refer to as the dimensions. So if you really want to be able to understand much about matrices, all you need to be able to know is that how can we be able to identify a matrix. So a matrix normally is specified based on the number of rows followed by the number of columns. So for example, in this particular matrix, you can see we need to first look at the number of rows, which basically is what? First row, second row, third row. We also need to look at the number of columns, which is basically first column, second column, third column. Hence, we can call this matrix a 3x3 matrix, as you can see here. Then we can also have this matrix, which basically will have to do it. So let me just first use the pen here to explain that. So basically that. Okay, so this is basically what we are referring to as what? A 3x3 matrix. Now, when you come here, we want to be able to look at it in the form of what? The number of rows. And if you check well, the number of rows are basically this and that. So there are two rows. The number of columns are this: 1, 2, 3, and then 4. Hence, we can call this matrix a 2x4 matrix, as you can see here. So this is basically a 2x4 matrix, sorry. So let me just join it to. Good. And lastly, we can look at this particular one, which is a single row matrix. And you and I know that from the previous slide, if it's a single row matrix, we call it a vector. Again, if it's also a single column matrix, we also call it a vector. So with this, we know this is just a single row, hence we have a 1 by what? And for us to know the number of columns, we just have to count them. So 1 and then 2. So this one gives us what? A 1x2 matrix. So that's it here. All right, that's it. So that's how we actually label matrices. We label matrices based on the number of what? Rows, followed by the number of what? Columns. That gives us how we can identify what the matrix is. Now, when you come to this particular side, basically what we are saying is that matrix is denoted by a bold capital, right? In other words, an uppercase letter. And then the elements within that matrix is normally denoted by lowercase element. So the main matrix is what? Cap A. The dimensions basically is m rows by n columns. Or we can have a subscript m, then the name of the matrix, and the superscript n, where m will be the number of rows, n will be the number of columns. Now, within that, we have what we refer to as the aij element. So the aij, basically, I will deal with the row, j will deal with the column. So if I am at the first row, then I can have A1J. So you can see that the 1 is maintained in all cases, right? But at the end, what is changing is the J. The J is now 1, 2, 3, 4, all the way to N. Similarly, if I come to the second row, I'm going to have A2J. So what basically is going to be maintained is actually going to be dealing with what we refer to as the 2s, right? Which is basically the i's, the number of rows, right? Or the row number. And then what is going to change, it basically is going to deal with what? The j's, which is the columns. So 1, first column, which is 1, second column, which is 2. If there's a third column, all the way to an ijth column. And then we can have all the way to the nth column. Then we can go even to A31, A32, A33, A34, all the way to A3N. Then lastly, we can also look at what we refer to as a the last row, which is basically AM1, AM2, AM3, all the way to AMG, and then AMN. So basically that's it. So that's how we're able to identify the number of rows with the number of what columns. Okay. Now, with that said, we can now look at the various types of matrices. So for us to be able to understand the types of matrices, we need to be able to look at it in terms of first the column matrix, right? Which basically we know is a vector. So a column matrix will have a single column followed by number of rows. And then we can have what we refer to as a row matrix, which basically is also a vector, which is also going to be a single row followed by respective columns. That's it. So with that said, we are okay with these two types. Let's move on to the third, which is basically going to deal with a rectangular matrix. So for a rectangular matrix, all we are saying is very simple. We want to be able to look at it in terms of the number of rows not being the same as the number of columns. So the number of rows is the same as the number of columns, then what we have on the table is that we are now dealing with what a square matrix. So for square matrix, the number of rows is the same as the number of columns. But for a rectangular matrix, the number of rows is never the same as the number of columns. Okay, so just a recap, with this particular matrix, we can probably be able to say that we can identify it as what 1, 2, 3, 4, a 4x2 matrix. And this we can identify it as what 1, 2, 2 by 1, 2, 3, 4, 5, a 2x5 matrix. If you come here, this is a square matrix, you can identify it as a 2x2 matrix. This is also a square matrix, we can identify as a 3x3 matrix. Why? Because there are 3 rows, 3 columns. Okay. Then from there, we can now look at a diagonal matrix. So the relationship is that from the square matrix, we can look at a diagonal matrix. With the diagonal matrix, is also a square matrix. But this type of square matrix, we have only the main or the leading diagonal element having values. The off diagonal, which is this, and then that, are zeros. But the leading diagonal elements, this 1 and 2, basically will have elements. So this is a 3x3 diagonal matrix. This is also a 4x4 diagonal matrix. But at the end, the main diagonal element is the one that is being suspended from the top left to the down right. Okay. With that said, we can now look at a unit matrix or unit to identity matrix. Now we talk of unit to identity matrix. All we are saying is that we want to be able to still have a diagonal matrix, which is branching from a square matrix. Now, with that diagonal matrix or the square matrix, all we are saying is that the diagonal elements should only be unity or should be 1. And of course, off diagonal elements will definitely be zeros. So that is it about the unit or identity matrix. Now, when we are done with the unit identity matrix, we need to look at what we call the scalar matrix. Right? So before I come to the scalar matrix will still be the same as the diagonal matrix, right? But this time around, the main diagonal element is a single value. So if the scalar is 7, then that means that all these Aij will only be 7. Now, so like this example that we have 6, 6, 6, 6, which is a 4x4 matrix, right? In other words, a 4x4 scalar matrix. When I factor out the 6 here, I'm going to have a unit matrix here. So that if I multiply the 6 with the entire matrix, the whole of this will be 0, this will be 6, this will be 0, this will be 6, 0, 0, all the way to the last diagonal element, which is going to be also 6. So with that said, for scalar matrix, it has to be first a square matrix, it has to be followed by an identity matrix. It has to also go ahead to look at what we refer to as what the scalar matrix, whereby I can have a single value representing all the diagonal elements. And when I factor that single scalar out, I'm still going to have what we refer to as the identity or the unit matrix. Watch this. If the 6 comes out here, This whole thing will be 1. Of course, for the null matrix, it doesn't need to be square matrix, it doesn't need to be rectangular matrix. It can be any matrix at all that has 0 elements inside. We call it the null matrix or the 0 matrix. Any of them works. Then we look at the triangular matrix. So for the triangular matrix, because we want to be able to establish a symmetry or line of symmetry from the diagonal element, we normally always expect the triangular matrix to be a square matrix, right? So this square matrix will have the upper triangular matrix to have elements. It might not necessarily be zeros, it might not necessarily be ones, but it should have elements. And then the lower triangular matrix should be zeros. Now, if I go to the lower triangular matrix, the vice versa holds here. The lower triangular matrix should have elements, the upper triangular matrix should be zeros. So a typical example is what you are having here on the table. So at the end, you will not have any issue in terms of trying to understand how things go when you are dealing with what? Matrix multiplication as well. Now, for equality of matrices, 2 matrices are said to be equal, right? Only when all corresponding elements are equal. So you want to check whether matrix A is the same as matrix B. In other words, it's equivalent. Then we need to be able to check first the dimensions. The dimensions are all 3 by 3, which is good. It can be 3 by 4. In other words, 3 by 4 from the other side. Then we can now compare this first element to that, 0 to that, 0 to that, 2 to that, 1 to that, 0 to that, all the way to 3 to 3. If you're able to get it done, then we can now draw a conclusion that the 2 matrices are the same. Now, some properties of equality. If A equals to B, then B equals to A, then all A and B, right? We can say that B is equal to B because it's for all A and B. What we are trying to say is that if A is equal to B and B is equal to A, then we can say the 2 of them are equivalent. If A is equal to B and then B equals to C, then we can say A will also be equal to C, which is true. This is a simple logic. If A contains 1, then B contains 1. If B contains 1, we obviously say that C also contains 1. So at the end, we can say A is also equal to what? C, because they are 1, 1. Let's look at addition and subtraction of matrices. So for addition and subtraction of matrices, we add matrices which have the same dimensions. It doesn't necessarily need to be square matrix or rectangular matrix. No one cares. All we care about is that it has to be having the same dimensions. So if I'm adding a matrix A 2 by 3, then a matrix B should also be 2 by 3. If I'm subtracting a matrix 2 by 3, then a matrix B should also be 2 by 3. Please, are we okay on that? So with that said, we can easily be able to have a 7 added to 1, giving us 8. 3 added to 5, giving us 8. -1 added to 6, giving us +5. All the way to -6, -5, let's say, added to -2, giving us -7. Then I go here to 6 added to 3, giving us 9. And then 2 added to -4, giving us -2, right? Now let's look at the matrix multiplication. So for matrix multiplication, just give me some 30 seconds, right? I'm coming. Okay, let's continue. Now, for the matrix multiplication, it's not the same way we are doing matrix addition, right? Where the dimensions should be the same. For matrix multiplication, the main thing is that we need to have a rule that we need to follow. And that rule is that the inner dimensions must agree. And what does it mean to say the inner dimensions agree? What it means to say the inner dimensions agree is that all we are saying is this. If let's say I'm multiplying two matrices, A and B, right? For the inner dimensions to agree, which is basically the same as saying they must be conformable, right? Then the number of columns in the first matrix A should be equivalent to the number of rows in the second matrix B. So for example, I'm going to multiply matrix A and then matrix B. Matrix A has a dimension of 1 by 3. Matrix B also has a dimension of a 3 by 1. So for it to be conformable, then what we are saying is that the number of columns in the first matrix A should be the same as the number of rows in the second matrix B. Now, with that acceptable, then we can say that these two matrices are conformable. So when we say the inner agrees, it means that we are picking the inner dimensions, these guys, and basically they are all expected to be the same. So 3, 3. And then at the end, we can now pick the outer values, which basically is 1, 1. So anytime you have a particular matrix and then you want to multiply with another matrix, the first thing you need to do is to look at the dimensions and check whether the inner agrees. When you look at transpose, you realize that some of the things will change. So the inner dimensions might not agree, but sometimes when a transpose is introduced in one of them, it should change the dimensionality stuff. If let's say the matrix is 2 by 3, once I transpose it becomes a 3 by 2. Okay, now let's see why this is not possible. So for this, the dimension of B is 2 by 1. The dimension of A is 4 by 2. Realize that these guys are not the same. Hence, we cannot multiply them. When I come to A, B, right? A is 6 by 2. B is 6 by 3. So these guys too. And lastly, we have a matrix of 2 by 3, another matrix of 3 by 2. If you check well, this one, the inner agrees. So that's what you get here. Okay. So that's good. With that said, we can start with the matrix multiplication. Any questions so far before I move on to the matrix multiplication? If you have a question, please, you can raise your hand. Okay, so since there's no question, I think we are all good. Now, if you want to multiply two matrices, let's say matrix A, which we know right now is a 2 by 3, and the matrix B, which is basically a 3 by 2. So at the end, we know that our answer is going to have the inner agreeing. So you're going to left with what, a 2 by 2. Okay. So how do you do it? We use what we call the 7th rule to do that. So first thing we have to do is that we need to pick the first row here and then concatenate it with the first column here. So that's going to give us A11 times B11 plus A12 times B21 plus A13 times B31. That's the first time. When you do that, that should lead you to here, which basically give us a C11. Now, with that said, we can now move on to look at the next thing, which is now going to be the same as A1112 going to the second column here. So what do we have? It's going to be A11 times B12, which you can see here, plus A12 times B22, which you can also see here, plus A13 times B32, which you can also see here. And that should result to you in the C12. And change the color. You go to the second row in the first matrix. So we pick this.
Hello, sir.
Yeah.
Please, can you take it again? Like
Please.
from the 3x2 matrices.
You mean this side, right?
Yes.
Okay.
How you concatenate it with the 3x2, the 2x3, concatenating with the 3x2, getting C11.
Okay. All right, that's fine. So first thing I mentioned, we have to make sure that the inner agrees. Okay. So once you have like 2x3 for the first matrix, 3x2, you realize that this 3 agrees with this. So I'm going to have a final thing as the extremes 2x2. So our answer is going to be a 2x2. So what I did was that I started with the first one with a green line, A11, A12, A13. And then I concatenated with the first column in the second matrix, which basically is B11, B21, B31. Now the concatenation is very simple. It's going to be A, let me see whether I can pick that green marker one. It's going to be A11 multiplied by B11, and that's what you are seeing here.
Okay.
Plus, now you pick A12, you're going to pick B21, and that should give you this.
Mm.
And lastly, you're now going to pick A13 and B31. And that should be this. So when you finish, you can get C11.
So that is where I'm confused. The C, how you've gotten the C11?
Oh,
Because
it's a dump.
in the matrices there was no C.
Oh, I get where you're coming from. So it's just an example, just a generalized thing. So we're going to use a real example to explain. Okay.
All right.
Okay, I get where you're coming from. All right, so let me quickly finish with this, those who are following me. So when I come to the second row, please, the one who asked the question, I'll use an real example to explain, then you follow, right? So we're
Okay,
going
sir.
to, this one, this first row, it is, which basically is going to be A21 times B11 plus A22 times B21 plus A23 times B31. And that should give you your C21. And then lastly, you're going to pick the same second row and then the second column in the second matrix. So that's going to give me A21 times B12 A22 times B22. And lastly, A23 times B32. Okay, that should give us what we refer to as a C22. But quickly, let's look at the real example and follow it there. So you have two matrices. The first matrix is what? A 2 by 3. But there are two columns. So 2 rows, 3 columns. And then this one is a 3 by 2. Basically, there are 3 columns, 3 rows, and then 2 columns. So with the 7th row, I can start with this. The one who asked the question, if you want to get a C11, it's going to be 1 times 4, which is 4,
Yes, sir.
plus 2 times 6, which is 12. 4 plus 4 gives you 16.
Yeah.
Then 3 times 5 is
15.
15. So 15, 16, 31. That's it here.
Okay.
So with that said, we are okay to go. Do you understand?
Yes, sir.
Okay, so then we can do the other one, which is also going to be the same as the 1, 2, 3, concatenated with the 8, 2, 3. So let me pick a different marker there. This one. And then that's. So that's going to give us 1 times 8, which is this, plus 2 times 2, which is that, plus 3 times 3, which is that. And when you do that, you should be able to get your 21. And then now, we can now go ahead and look at the other one, which basically should be the second row, which is 427 against 465. So 4 times 4, which is this, 2 times 2, 2 times 6, sorry, which is this, plus 7 times 5, and that should give us 63. And then lastly, we can now look at, let me pick a different color, maybe red, yeah, red will work. I can now pick the same 427, the 7 through, then go here, and that should be 4 times 8, which is there, plus 2 times 2, which is there, plus 7 times 3, which is there. And when you do that, that should give you your 57. So far, so good. Any question? Okay, so another thing we need to know is that if I have any matrix A and I multiply it by the identity matrix, I should get the same matrix A. Okay, like what you see here, right? 1, 0, 1, 0, 1. And then I multiply it with the matrix A with 31, 32. So 31, 21, 63, 57. And then at the end, I can get the same 31, 21, 63, 57. Okay. Now let's look at matrix operations. So for matrix operations, we want to be able to, so we just saw this one not long ago, okay? But the other one to have to do with associative law, which basically is dealing with the fact that if we have A, B, C, we can deal with the B, C separate. When we finish multiplying that, we now have the A multiplying the B, C. And then later we can now have AB. And then we can also have the C. So whatever we get for AB, when we are done, we can now also concatenate it with the C. And that give us ABC. Then we can go look at the first distributive law, which basically is going to deal with what you adding, before you add the A and B, you first distribute the A. Before you add the B and C, you first distribute the A over the B, which will give you AB. Then also distribute the A to the C. That will give you what? AC. Now we can look at the second one, which will now deal with the C distributed over the A, and then the same C distributed over the B, and that will give you AC plus BC. Okay. So another thing you have to know is that when you have A, B, it is not necessarily as BA. You cannot always be doing that. So we will show that shortly. I think let me go back and show you something. So you see this one, which is a 2 by 3, and this is a 3 by 2. But this particular one will work because if you have a 3 by 2 and a 2 by 3, that will work. So there are instances whereby you have a 3 by 2 and then another one will be a 3 by 1. So when you switch it to not work, and that's why we are saying that it's not always the case that you can have AB, that will always work, right?
Yes,
And then if AB is equal to 0, then we are not always saying that A should be 0 and then B should also be 0. And lastly, if AB is equal to AC, B will not necessarily be the same as a C. Now, let's look at the transpose of a matrix. So, for the transpose of a matrix, we can now have it in this way. If I have, transpose basically is referring to you making sure that you have the rows now becoming columns and then the columns now becoming rows. That's it. When you're looking at transpose, all that you are doing is you are just switching them. All we want to be able to get is that we have the row now becoming the column, and then the column now becoming the row, right? So in this case, if I want to transpose this matrix, the row 247 will now be this. The row 532 will now be a column here. Basically that. So that's it. If I transpose, you're just interchanging the rows and the columns, right? So the properties are A plus B all transpose will be the same as A transpose plus B transpose. And then AB transpose is going to be the same as what? B transpose, A transpose. It's not the same as A transpose, B transpose. So these are proven properties that you can actually be able to show and then try it and work with some real examples. Again, we can also have the KA transpose, which is going to be the same as what? K A transpose. And then the last thing is that if I transpose a particular matrix twice, I should get the same matrix. Okay. Just a second. Please hold on a second for me.
sir.
Yeah.
Sir, please, a second. You said for the 2 by 3, at the if 2 by 3, the first one, you said you change it to column, right?
Yeah.
Yeah. So will you get the same answer for both?
You mean will you get the same answer for both?
Yeah.
How? You
Like
mean the
maybe
first
if
one?
you are working it out, will you get the same answer for both?
And when you say working it out, you are transposing, you are not working, you are just trying to change the position. So when you say you get the same answer, it depends on where you're coming from. If you are having, let's say, A and B added,
Yeah.
right?
Yeah.
You are having A transpose added to B. you might not get the same answer because when you transpose that A, which initially was, let's say, 2 by 3, when I transpose the A, it now becomes a 3 by 2,
Yeah.
which might not even be feasible to add on to a B, which is also a 2 by 3.
Okay.
So the transpose is just there in the case whereby we are really in a different situation, whereby we need to be able to transform the rows and the columns to make it work. That's where the transpose comes in.
Okay.
Are you okay?
Yes, sir. Thank you.
All right, good.
Yeah. Hello, sir.
Yes, please go ahead.
Please, with the property 2 and then 3, do they have, any qualities being similar or they are independent, please?
The property A, which one?
Property 2 and then 3, the transpose side, please.
Property 2 and 3, do they have the
Yes.
same?
So do they have similarity or they are independent, please?
No, they are not. They are not similar. The K here is a scalar, so it can be a number. Okay, but this A is a matrix, B is also a matrix. But here it's only A which is a matrix. The K is not a matrix, it's just a particular scalar which is like a number. So if you go back to, let me just draw you guys back small. If you see this guy, right? Here, which we are calling a scalar matrix, I can actually bring out a 6 out here, and the whole of this will be unity 1. So in this case, I can actually have a K with an I, whereby here the K is a 6, the I will be the unit matrix.
Unit
That's
matrix.
what
Okay.
unit matrix is here.
Sir, please, why are you factorizing the 6 out to get 1, 1, 1?
Well, because I was just using it to show the example you asked about the KE.
Okay.
And if you factor it out, it's the same thing. Because this is the same value, 6 throughout. So if I factor 6 out, I can actually multiply that through by the 6. And that should give me the same value and the same matrix. Okay.
Thank you.
You're welcome.
Yeah, hello.
Yes.
So can we use the transpose when we are multiplying a matrix and then the columns are not the same? For example, a 2 by 3 by a 3 by 2. If you're multiplying them, since we want the inner sides to be the same, is that the case where we use the transpose or we use it in a different scenario?
You said 2 by 3 and then?
Yeah, and then a 3 by 2 matrix.
By the 3 by 2.
Sorry. Okay, so the other way around, and then 2 by 3, yeah, and then we have to multiply them.
Good. So in this case, let's say we are transposing, let's say this is A. And let's call this a B. If I transpose the B, I'm basically going to have a 3 by 2, right? Which will work. So in this case, since AB will not work, I can rather have AB transpose, which will make sense.
Oh, nice. Sure.
Please, do you understand now?
Yes, sir.
Okay, sure. Let's move on. So there's some in-class exercise for you. So this one, I just want you to pick some dummy examples of your own, right? And then maybe try and see whether you can prove it. So just get a particular matrix A, give it your own dimension, whether you want to have a 2 by 2, a B to be a 2 by 2, add them first, and then transpose. Then that A you pick, which is a 2 by 2 matrix, transpose it, and then B, which is a 2. Okay, this one might not work. So let's say we have a 2 by 3. Let's try a 2 by 3 rather. And then B is also a 2 by 3. You add the A and the B, you get a 2 by 3. You transpose it. That should give you a 3 by 2. Now this one, which is what? A 2 by 3. This is also a 2 by 3. Transpose the A, probably, which is 2 by 3, will now be 3 by 2. Transpose the B, which is initially 2 by 3, will now be 3 by 2. And then add them after transpose. And let's see whether you get the answer. And then when you're done, you try the same thing on this, right? So use real examples to make it work. Yeah.
Sir, please, will you give us the numbers, or we should use our?
No, try your own numbers, but don't use a square matrix. Okay.
Okay.
All right. So just 5 minutes, give it a try and let's see.
Okay, so
Hello, sir.
so 2 by
Voilà.
Hmm?
Là, on a coup.
Okay, so continue. I don't know why some of you want to write on the screen. Please stop that, okay? All right, so if you have done that, let's try and look at the examples I have, and then you can compare with yours, right? So for example, the first one, this is what I have. And then that's the second one. So the first one, I use a 2 by 3, and this is also a 2 by 3. Then when you add those 2 by 3, 2 by 3, you're also going to get a 2 by 3, which is basically this part. That's it here. When I transpose it, I'm going to have this, and that's a transpose there. So when I come to, so this is the left-hand side. And when I come to the right-hand side, basically for the right-hand side, all I'm going to do is I'm going to pick this one, the A, transpose it. So when I pick the A, I transpose it, that becomes this. Because if I transpose 7, 3, negative 1, 2, negative 5, 6, I'm going to get 7, 3, negative 1, 2, negative 5, 6. And then when I also pick the B and I transpose it, that's also going to give me 1, 5, 6, negative 4, negative 2, 3. Then now I can add them after transposing. And if you check, you're going to get the same thing like this one, right? So the right-hand side should be the same as the left-hand side, which you have done initially, okay? So that's it with this. Then when I come to the similar example, but this time around, because if you have 2 by 3, and then this is a 2 by 3, it will not work. So I pick another example, which is a 2 by 3, and then this, which is what a 3 by 1. So this is 2 by 3 for A, and then a 3 by 1 for B. So realize that the inner agrees. So at the end, I'm going to have what? A 2 by 1. Sorry, that 2 by 1 should be here rather. Okay, and then when I transfer, that'll give me a 1 by 2. Okay, so what does it mean? All we are saying is that we're going to first multiply the A and the B, which is going to give us a 2 by 1. When I'm done, I'll transpose a 2 by 1, which is a 2, 8, and that'll give me a 2, 8 on a single row. That is it for the left-hand side. Now, when I come to the right-hand side, our main focus is instead of having A times B, I'm going to have a B transpose multiplied by an A transpose. And why is it so? If you do A transpose multiplied by B transpose, it will not work. Okay, so it will not work because if I transpose A, I'm going to get a 3 by 2. If I transpose a B, I'm going to get a 1 by 3. 3 by 2, 1 by 3, the inner doesn't agree. So that's why we have it to be what? A B transpose. And B transpose should give us, instead of 3, 1, will give us a 1 by 3. So that's for the B. If I pick the A and I transpose the A, 2 by 3, transposing will give me a 3 by 2. Now this inner agrees, the 3, 3 agrees. So I'm going to have what? A 1 by 2. And that 1 by 2, which is basically for the right-hand side, is the same as the left-hand side, which also gives us what? A 1 by 2 of what? 2, 8. So you see that this 2, 8 is the same as this 2, 8.
Sir, please, can you repeat the question 2 again?
The question 2 says that pick an A, pick a B, right? Transpose before that, multiply them and then transpose. Then when you are done, switch the A and the B. That'll give you a B and A. This time I want transpose the B, transpose the A separately, and then multiply them. So whatever example you are using to prove this, make sure that the inner agrees. So my example that I picked was a 2 by 3 for A. The other example is a 3 by 1 for the B. Now with that said, I was easy to be able to get the inner agreeing, the 3 and 3 agreeing. So that's supposed to give me a 2 by 1 when I finish the multiplication, which by now everyone can do this multiplication. So when I get a 2 by 1, the question says that after you have multiplied, giving you this 2, 8, right? Transpose it. So when I transpose 2, 8, I'm going to get this 2, which was initially 2, 8, initially a column, now becoming a row. So that's it after the transpose. So this is where the transpose resulted in. That is for the left-hand side. So I'm done with the left-hand side, which is this. Now when I come to the right-hand side, The right hand says that pick the B is 1, 1, 2. Transpose it. If I transpose column 1, 1, 2, I'm going to get row 1, 1, 2. Then pick the A which is was 1, 1, 0, 0, 2, 3, and transpose that particular A. If I transpose the A, the whole of this first row will become a first column here. The whole of this second row will become a second column here. Then what do I have? I have the B transpose here. I have the A transpose here. You realize that here the inner will agree. This is 1 by 3 after the transpose, 3 by 2 after the transpose. Since the inner agrees, I'm going to have the resulting value to be what? 1 by 2. And that is what we are having here at the right hand side.
Okay, sir.
So I think we can move on now. I'm sure you all got it right. Please, if you didn't get it, it means that the you use were having an issue. Yes, someone want to ask a question. Go ahead.
So I didn't get a question. Well, I joined. I off and I joined again.
You didn't get a question 1.
Yes,
Question
please.
1, can examples. So I'm just asking you to prove. This proof I'm asking you is not proving. Just use examples, rare examples to prove that. So the example we used was matrix A is this form, matrix B is that form. Okay, so the only thing I mentioned was that don't let the dimensions of A and B to be the same, right? Just switch the dimensions. So look at all rectangular matrices, all right? So that's the example.
Okay.
So first look
Hello,
at
sir.
A and B, add them. When you finish, this is going to be the first addition. When you transpose, you're going to get this. Then be for the left-hand side. For the right-hand side, it says that the A, which is this, transpose it, and that'll give you this one. The B, which is this, transpose it, that'll give you this. Transposing the B means that the first row will not be a first column. The second row will not be a second column. So when you're done with that, you add them. And that will give you what I've said, which is equivalent for the right-hand side, is equivalent to the left-hand side initially proven.
Okay. Thank you.
All right. Prince, I see your hand up.
Yes, sir. So please, I wanted to ask, the options I chose to go with for the transposing, that's in the second one, the number of columns, there was 1 column and 2 rows for A, and then for B as well, it was 1 row, 2 columns. But when I was doing the transposition, then I realized that the number of rows and columns, I think for multiplication, as you mentioned earlier, there should be an equal number of rows in A as there will be columns in B. But then it couldn't put it that way, so I put the multiplication for that.
Yeah, so because it didn't work that way, you need to change your example.
Okay, so it's the example I chose.
Yeah, it's the example we chose. The
Thank you, sir.
dimensions
Hello,
you
sir.
chose. Yeah.
Thank you very much.
Patrick, your hand is up.
Hello, sir.
Yeah, sir.
Please, let's comport ourselves. If you want to talk, raise your hand, please. Patrick, please go ahead.
Hello, sir. Please, what about a 3 by 4?
Patrick, okay, Edu, your hand is up. Please go ahead. Patrick is not ready. Joshua, I see your hand up. Please go ahead.
Hello, sir.
Yeah.
So please, how would you know that after multiplication, this is the type of matrix you get? Maybe 2 by 2 or 2 by 1. How would you tell?
Oh. So this example you have seen right now, see the 2 by 3 for A, the B 3 by 1. If the inner agrees, right? See something. This goes away. What is left? 2 by 1. The outer.
Okay. So
See,
that's how we should tell. Okay.
yeah. So that's
All right.
outer will let you know whether you're on course after your multiplication. So because I know that my final answer should be a 2 by 1, if let's say mysteriously I get a 1/2, it means I didn't do something right.
Okay.
Please, I hope you get it.
Yes, sir.
All right, sure. Okay, I don't see any hand up, so I think we can move on, right? Let's look at the inverse of matrices, right? So for inverse of matrices, all we are saying is that so there's something that's not part of the slide. Let me talk about it, so maybe pay attention here. So there are some other forms of matrices which we call the singular and non-singular matrices, right? So when you talk of a singular matrix, it's any matrix that the determinant is 0, right? If it's a non-singular matrix, then the determinant is not 0, right? So that's the first thing we need to know. So singular matrix the normal singular you have, right? But there's nothing like plural matrix. It's rather singular or non-singular. Okay. So for singular, let me write the non-singular here. That is why I'm saying that the determinant is 0. I'm here to teach the determinant, so please pay attention shortly, right? Okay. So with this one, we can say that the determinant of that matrix A, if you want to use determinant, you can use this from this thing, right, to represent a determinant, or you can also use this. So for singular, the determinant should be 0. For non-singular, the determinant is not 0. It's any other value apart from 0. It can be a negative value, it can be a positive value, but it can never be 0. Now, why did I bring this in? I brought this in because if you are trying to find the inverse of a matrix, then that particular matrix should be a non-singular matrix. So that's why it's the first point of call when you're finding the inverse of a matrix is to be able to look for the determinant. If you find a determinant and the determinant is 0, then you conclude that the matrix is singular, hence the determinant doesn't exist. If you find a determinant of that matrix A, and then the determinant is, let's say, 3, then that means that the inverse of the matrix exists. So you can go ahead and find the inverse. So what's the inverse formula? The inverse formula is normally giving us 1 over the determinant of that matrix A multiplied by the adjoint of that matrix A, or sometimes we call it the adjugate of the matrix A. And then the adjoint or the adjugate is normally giving us the cofactors of that matrix A or transpose. And to get the cofactors of that matrix A transpose, you need to be able to find the minus of that particular matrix A, right? So first, let's look at how we can find the determinant of a matrix. So to compute the inverse of a matrix, the determinant is required. It's a key requirement, right? Each square matrix A has a unit scalar value called the determinant of A, denoted by determinant of A or this particular symbol, right? Now with this, the application of this is going to help us. Remember, I mentioned that one of the key applications of matrices is trying to be able to solve a linear system of equations. So if I want to solve, let's say, 20 systems of equations, I can easily be able to convert them all into the form AX to be equal to B, right? So back in your senior high, remember your simultaneous equations you were doing, right? So in the university, we can model a particular equation into a set of linear equations, right? Let's say 20, 30 thousands of them. And then all we're going to do is, let me come to a lower level explanation, maybe 3 equations, right? So with that 3 equations, I can easily be able to find the A. The A would be the coefficient matrix. So that coefficient matrix is going to probably have what is the coefficient value of the X, the coefficient value of the Y, the coefficient value of the Z. So that X, Y, and Z will actually be the column matrix for this particular X, which you call the unknown variables. And then the values in front of them will actually, in front of the variable X, Y, and Z. If you want to use X1, X2, X3, that's fine. So the coefficient values in front of that X1, X2, X3 will now go into to form this coefficient matrix A. And then the values that are after the equal sign, right, on the right-hand side is what we refer to as the known variables or the known column matrix or the known vector. So at the end, we can now establish them like this. So what do we have? We know X, we know A, we know B values, but we don't know X. So our key thing is to be able to make X a subject. So making X a subject cannot be X equals to B over A. No, that's not just done. But rather what we do is that we can find A inverse and multiply it by this. And then we can also have A inverse multiplying the B. So that the A inverse and then the A will give us what a unit matrix. And then we can have the A inverse multiplying the B here. So in that case, I'm going to have identity I multiplying the X. And we know an example that an identity matrix multiplying an X will always give you that particular X variable. So it's going to give us X to be the same as the A inverse multiplied by B. Now with this said, all we are saying is that that's a key reason why we need to be able to look for the inverse of a matrix. Because if you don't know the inverse of a matrix, then when you are trying to model, let's say, a satellite dish with some systems of equations, there's no way you can be able to find that X, which can be used to be able to solve that equation. It's not going to be possible. So once we know how to find the inverse, we can actually be able to write our codes in Python, in MATLAB, in Octave. And then when we are done to find that inverse, we multiply it by the known vector. That's it. And then that will give us the unknown variable values. All right. For the basic 2x2 matrix, which back in the senior high you learned it, it's just finding the determinant as 1 times 5, then minus 2 times what? 6. That's the basic stuff you guys learned back in the senior high. So in that case, everyone knows that the determinant of this particular 2x2 matrix is going 1 times 5, which is 5, minus your 2/6, which is going to give us minus 12. And that should give us a minus 7. And once you get a minus 7, that minus 7 is a non-singular matrix. Hence, the determinant is not singular. It's a non-singular matrix. So the inverse will exist. Remember, I said that the inverse is 1 over the determinant. So if the determinant is 0, then the inverse of that matrix does not exist. So for 2x2 is easy. Let's go with the 3x3. So for the 3x3, now we can return into 4x4. Let's see how it's done. So for a 3x3, finding the determinant. Once we understand the determinant aspect of it, it will be easy for us to also identify the minus. So we give a typical example. Let's use this example to find the determinant. The first thing I need to do is that I need to be able to pick this, cross it out, and then it will now reduce this matrix A into a 2x2 matrix. So for 2x2, I know that I'm going to have 2 times 1, which is 2, minus 0 times 3, which is going to give you what? 0. So that's going to give us a 2 minus 0. But what did I do? You realize that I crossed this guy out. So there is a 1 here. So I'm going to use that 1 to multiply this. Okay, so I'm going to have 2 minus 0, that give me a 2. Then that 1 here will be used to multiply it. Then let's go to the next one, okay? So I come to this side, and then I cross. Now, when I cross this, that is going to give me 0, 3, negative 1, 1, okay? So let me just do it this way. So now, I'm going to have my 0 here, and then there's 0, negative 1, 3, 1. So I'm going to have 0 times 1, that will be 0, which is this here. Minus is already there. I'm going to have negative 1 times 3, that'll give you negative 3. So at this situation, this was supposed to be 0 minus negative 3, which is basically 0 plus 3. Then the last part of it, let me use Word, is to be able to cross it in this way. I'm going to pick this one, which is this. Then I'm going to have 0 times 0. Then I'm going to have minus -1 times 2, which will give you -2. And because there's already minus there, so that'll be +2. Now I'm not done. The last thing I have to do is that in determinant, I always have to start with a plus here. Go to the minus. So in that case, where the 1 is, we'll have a plus in front of it. And that's why where the 0 is, there's a minus. So this minus as a result of what is here. And then where the last 1 is, there's also a plus. So at the end, that should give you a 4. Any question on finding the determinant?
Yes, sir.
Prince, your hand is up.
Yes, sir, please. For the 3 by 3, it went right over my head. I've been trying to follow, but I seriously can't understand anything. So please, sir, could you take it one last time?
Okay. All right. So before I take, let me listen to the others. Patrick, do you have the same concern?
Yeah, sir, it's the same thing. I just don't understand anything.
Okay. Minta Daniel, how about you?
Okay, so for me, it's about adding. And for the plus minus plus, we will first like find the possible answer before we add the plus minus plus, or we add before we sum them together.
Yeah, you can do it any way you want it, provided it's not having any challenge with it, because that's the final one that comes in. Okay, you realize that it comes in after you put in your values, then that is what you're going to use to concatenate all the 3. So don't add it on the table as it stands now, so that you don't get confused. If the year is plus, minus, you do this, and probably this one becomes minus, this become positive. No. So it becomes the last minute thing you do.
Yes, so I'm talking about the last minute. Look, the 1 minus 2, 1 times 2 minus 0. Like we will first solve it. Then maybe if it is the answer becomes negative, then we change it to positive. That's
You
one
mean
thing.
this part?
Yes.
Yes. Without you introducing the plus minus, you can't get your 4. So you can do it alongside. So when you are done here, you can bring the minus, you can bring the plus. Normally what I do is I leave the spaces in between them. When I'm done writing it, then I go and do my plus minus, and then I put it inside, so that it doesn't confuse me.
Okay.
But the interesting thing is that this one the calculator can do for you. So please learn how to use the calculator to do it. The calculator can do up to 3 by 3 matrices.
Yes,
Okay.
sir.
All right. Should I take it again? Vida. Yeah.
Yes,
Go
sir.
ahead.
Sir, please, after adding, I had -4.
Oh, really? Check it all. You get the same values you're having here. 1, 2.
Yes.
This is and then this guy is 2. So even this is 2 plus -3. That'll give you -1. Okay. And then that's this is 2. Let's see. So this is what 1 times 2. That'll give you what 2.
2.
The whole of this is 0. Can you see
0.
that? 0. And then the whole of this guy is +2.
Okay, so why am I having the negative?
So that's 2 plus 2. That'll give you 4.
Yes, sir.
Okay, please check your side row.
Okay.
Ebenezer. Ebenezer. All right, so if there's no question, let me go over
Hello,
it.
sir. Please kindly repeat the process for. Hello, sir. Please can you repeat the process for finding for the determinant of the matrix A?
Okay, sure. So I'm going to do that, right? All right, so let's look at it again. Let me see whether I can clean. Okay. So this time around, what I'm going to do is that I'm just going to make sure that if I do one, then I'll clean so that you can follow. So I'm going to start. The first thing I'm going to do is that I'm going to pick this one. I'm going to pick that. So what am I going to have? I'm going to have the determinant of A to be the same as 1 here. Then I'm going to have my bracket opened. This is 2 times 1. That'll give me 2. This is 0 times 3. That'll give me 0. It's going to be 2 minus 0, which is what? 0. So I'm going to have this as only 2.
Hello, sir.
Please, you are following, right?
Hello, sir.
Yes.
Sir, please, why did we get 1 first before finding the 2 by 1?
So this one, there's a 1 here.
So the 1 we cancel.
Yes. It's not cancelled. It's just ruled to be able to let you have the remaining to find the minor or the determinant here. Are we okay?
Okay.
So when we are done
So-
with that, we can now move on and pick this 0 because that's what the next we are going to cancel. So that 0 will come here. Now, why is it minus? It's minus because I've already indicated plus, minus, plus. So this minus
Okay.
here is coming from here. So with that said, can now go ahead. This mute, please mute. This mute. And then pick this. Now when I cross it in that way, the 0 is already picked. So I'm left with 0, 3, negative 1, 1. So with a 0 there, I can open a bracket. Then I'm having a 2 by 2 matrix I can actually concatenate. So 0 times 1 is 0. Minus. Then 3 times minus 1 is minus 3. So minus 3 is going to be minus minus 3. So that's going to give me plus 3. These are we okay here?
Say,
Yeah.
say please, with the plus minus plus, does it always have to be plus minus plus, or you can
Always.
just, I don't get that side, the
Always.
plus minus plus at the top there.
Always. You can't change it.
Okay, so it's that static.
Yeah. Always you start with plus. You move on to minus, plus. If there's a 4 by 4, it will be minus. It's
Okay.
static. Okay. All right. So with that said, we are okay with this part. So that is a 0 here. Let me highlight that 0, which is this one here. Now, because we have the minus, which is already here, I can now go to the plus and pick the first row value, which is 1. And that 1 is this. So the next thing is I have to clean what is here. Okay. So I'm going to now cross this. So if I cross it, you realize I'll be left with what? 0, 2, negative 1, 0. And that is a 1 here. So I'll open my bracket. And I'm going to have 0 times 0. That give me 0. Then I'm going to have 2 times minus 1. That'll give you minus 2. And because it's already minus, it's going to be minus 2. So I'm going to have minus 2. So that will cross it to make it positive 2.
Okay. I get it.
These are we okay now?
Yes, sir.
Okay, so with that said, you can simplify. So this one will give you 2. This whole thing will give you 0 because of the 0 here. So it's going to be minus 0. And then this one will be 1 times 0 plus 2 will give you 2. So that will be what? 1 times 2 will give you plus 2. And that should give you positive 4.
Yeah.
Okay. So far, so good.
Sir, please. My question is, after when we are solving the determinants, after cancel the first row and the first column that we had 2 by 2 matrix, that's 2 and 2, 3 and 0, 1. So when we were multiplying by 2 by the 1, why is that the negative didn't affect the 2? Because the negative also in the position of 2.
This negative here is only this negative. That's why I said it's not part of the calculation. The rule says that when you are done and you're concatenating the values, so you see, that's where you can now bring in your plus minus. So I guess it is a plus here. Please, do you understand?
Okay, sir.
So it's not affecting the 2 here. So if you check the first example also, I didn't even introduce this negative and plus. It was after it was done, that is when I brought the negative and plus inside. Okay.
Yes, sir.
All right.
Hello, sir.
Daniel, Hannes, we just spoke. Benjamin Darkon.
Hello, sir.
Yeah.
Please, can we do 4 by 4? I want to see how the 4 by 4 be done. How we are going to cancel it.
That one I will let you do it a tutorial. If you do 4 by 4, I'll be behind. Okay. So, but it's the same logic you have to understand. So if it's 4 by 4, right? You cross it. You're going to have a 3 by 3 inside. And you find the determinant of that 3 by 3. So if it's a 4 by, anytime you cross, you're going to have a 3 by 3 like this. I hope you get it. And that 3 by 3, the same procedure we went through to find the determinant, you're going to use that to do that. But the main thing on the table is learn how the calculator can be used. The calculator can do a maximum of 3 by 3. Okay, so like what we are just done right now, maybe go online, just look at how YouTube can show you how to use the calculator to find a determinant, or even the inverse of it.
I understand the 3 by 3, but with the 4 by 4, when you cancel the rules and then the column, and then you get 3 by 3, and then you are finding the determinant. It means you multiply the diagonals and then.
No, you don't multiply diagonals. That 3 by 3 you're going to get is going to be like this. So the same procedure we are using to find a determinant manually, that's what you're going to use.
Okay, so you have to cancel the rules and columns again.
Yes, so if you cancel a 4 by 4, you get a 3 by 3. The 3 by 3 you're going to get, right? You're going to use the same procedure we are using here if you're doing manually to find the determinant.
All right.
Please, do you understand now? But this is a 3 by 3.
Yes.
You see the hell we went through to get a determinant of 4. If I want to use a 4 by 4 as an example for this class, I have to use like almost 30 minutes to find that determinant for each of them.
Yes, please, we get you.
You get now, right? So just try. The first thing I want to tell you is try and see how you can use a calculator to calculate the determinant of a 3 by 3. And that will help you. Even this one we are doing, if the calculator can be used, you're okay. Okay? Because you're not writing pen to paper exams, you are writing online on site. So in this situation, it's allowed to send a calculator to the exams venue if you're going to, if assuming this is going to assume, I don't know. Right? But as I'm teaching, I always don't teach you towards exams. I teach you to understand. Please you get it now, right? Okay, so that's it. Once you're able to get this, our first thing is that if the determinant is 4, which is letting us know that the matrix A is a non-singular matrix, hence we can go ahead and find the remaining part of the inverse because the inverse exists. All right, so the next thing we need to do is that we need to find the minus of that particular matrix.
Hello, sir. Hello.
Yes.
Yes, sir. I'm sorry to interrupt. I get the first procedure you showed us, but before you began, you also mentioned there was a formula to get the determinant. So if you could repeat the formula for us, I can try both techniques to see which is easier to find the determinant. You mentioned there was a formula for finding the determinant.
There was a formula for finding the inverse. For determinant, the formula is what you are seeing. If you want to generalize it, right? Then all you need to do is that the formula will not be static. It depends on the dimension of the matrix first. Why? Because if you are finding the determinant of this particular 2x2 matrix, the formula, assuming this is A, B, C, D, then the formula will be what? AD minus C, BC, right? For a 2x2. If you are dealing with a 3x3, that formula will change. If you are dealing with a 4x4, the formula will change. So there's no static formula for determinant of a matrix.
Sure.
But there's a formula for finding the inverse of a matrix. And that formula is giving us, so A inverse, which is denoted by this, is the same as 1 over the determinant. We know that now this is how the determinant can be written. Multiplied by the adjoint. And also call it the adjugate. So OINT, right? Of A. So this is a formula for finding the inverse of a matrix. Now, for us to be able to go to the adjoint of A, which is this part, we need to first establish that the determinant is not 0. Because if the determinant is 0, then we're going to have 1 over 0, which is undefined. And that will not be able to work for us here. So our main thing we have to look at is to be able to first check whether our determinant is not 0. If the determinant is 0, then we conclude that the inverse of the matrix does not exist. That's the first thing we need to look at. Okay. All right. So now we are going to look at the adjoint of A. Now the adjoint of A, from here, adjoint of A is given by the cofactors of A transpose. That's one of the applications of transposing. The transpose I showed you, if you're looking for the inverse, when it comes to the adjoint, you need to be able to find the cofactors. Cofactors is CO, then your normal factors, you know. So I'm just going to call it COF. Cofactors of A. Right? When you are done finding it, then you transpose it. So how do you find the cofactors of A? That's what we have got into. To find the cofactors of A, the first thing you need to do is you need to find the minus of the matrix A. The minus of the matrix A is what we are looking at now. So when you talk of the minus of the matrix A, so for example—
Hello, sir, please, I'm not getting what you are doing now. Please, can you start for me? Because I'm confused over there.
So we are not going there. I've not gotten anywhere now. I'm just trying to tell you that to find the cofactors, you need to find the minus. So that is where I am.
Okay, sir.
Please, you understand now, right?
Okay,
Now,
sir.
your minus, this is how you find it. The same way we are finding the determinants, you cross. Okay? Then you can find the determinant of what I've circled here. Okay, 3 by 3, which is easy, right? So it's going to be this times that minus this times that. The same way we're finding the determinant. So that will give us the first minus M11. I get him. So let's assume that I'm creating a particular matrix, which I'm going to call the minus of A. So maybe I'll put it somewhere here. So now please pay attention here. So that's what we call the minus of A. So I'm going to call it minus. And why am I finding the minus? I need to find the minus because after I get a minus, that is where I can actually find the cofactors of A. Without a minus, I cannot find the cofactors. So minus, let me add S here. All right, so the first thing is this, I cross, like the way I was doing the determinant, but the only difference is that I don't have to multiply this A11 with what is inside. Okay, so that's what you can see here. I'm going to have A22, A23, A32, A33. Picture them as actual values in the mind's eye. Okay, I'm going to use a real example, but first understand the logic here. So when I finish, I'm going to get a single value, right? And that single value, I'm going to write it here. Let's call it M11. You understand the first one?
Yes, sir.
Okay, so like this, if you cross here, you're going to have this. Okay, and then that's thing we're having here. Let me go back and use this example we're using. So I'll clean this one. This time around, forget about the plus and minus, okay? And then now I cross like this. So I'm going to get a first minor.
Mm-hmm.
I'm going to have this. Then I find the determinants. 2 times 1 give me 2. Minus 0 times 3, that'll give me 2. So the first minus should give me what? 2. There we go. So let me use this to find a minus so that we all can follow, right? So in that case, I can now come back here and then let me clean this. So let's use this example to find a minus so that we all follow. So the first minor, minus, let me get a space. Let me call the minor just M of A, which is basically saying I'm finding the minus of A, right? And this guy should be equal to this. What's the first minor? The first minor we got is what? 2 times 1, which is 2.
Yeah.
Minus 0 times 3. So at the end, the first minor will be 2.
2.
Are we good? Now let's
Yeah.
go to the second minor, right? So for the second minor, I'm going to clean what is here so that it will follow this there. Right? Then I'll pick the marker here. I cross this. I cross that.
So 0 times
So that will be 0 times 1, which is 0, minus 3 times minus 1, which would be what? Minus 3. But because there's already minus here, it's going to be what? Plus 3.
Okay.
So in that case, what will be here? 3. This you are following, right?
Yes.
Okay. Now let's go and look at the third minor. So I'm going to clean this. Then I'm going to pick my marker pen back. Then I'm going to cross. Then I cross this. So I'll be left with what? 0 times 0, which is 0. Minus -1 times 2. That'll give me -2. But because there is already minus, it's going to be +2. And this will give me 2. So I'm done with the first row for the minus. So this is M11, M12, M13. I'm left with the second row, which was M21, M22, M23. So that went to the same approach. So let's see how the cross will be done. Please pay attention here. So I pick that. And then because it's going to be here, right? This side. So I'm going to cross like this. And I'm going to cross like this. So I'll be left with 0, 1, 0, 1. So I find the determinant of that. That'll be 0 times 1. That'll give me 0. Minus 0 times 1 or 1 times 0. That will also give me what? 0. So the whole of this part will be 0. We good? So far, so good, right?
Yes, sir.
Yeah.
Okay. So let's move on to the next minor, which is going to give me M22. So I'm going to clean. And then I'm going to pick this. So the M22 will be here. So I'll cross. Sorry, cross row. Then cross. So I'll be left with 1, 1, -1, 1. So I'm going to have 1 times 1. That'll give me 1. Minus -1 times 1. That should give me -1. But because there's already minus here, it's going to -1. That'll be +1. And that'll give me 2. You go to the next minor, which will be this. So same here. Erase. And then pick this, cross. And cross like this. Well, let me just cross. Okay, good. So I'm left with 1, 0, -1, 0. So how do I go about it? It's going to be 1 times 0. That'll give me 0. Minus -1 times 0 should give me 0. So it's going to be 0 minus 0. So that'll give me a 0 here. So I'm done with M21, M22, M23. I'm left with M31, M32, M33. That's the last row for the minus. So what am I going to do? I'm just going to clean. And then do the last row. So first, I'm going to have it here. And I'm going to have it there. So this will give us 0, 1, 2, 3. So all I'm going to do is I'm going to have 0 times 3. That'll give me 0. Minus 2 times 1. That'll give me 2. So that should give me minus 2. Okay. Then I can now move on to the last but one. What I just did is the minor M31. I'm going to now M32. So for M32, it's where the 0 is. Then I cross on the 0. So I'm left with 1, 1, 0, 3. So that's going to give me 1 times 3, which is 3. Minus 0 times 1, which is 0. So that's going to give me 3 here. And then lastly, I can do the last minor, which is what is here, the one here. That's going to give us M33. So clean, 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 clean. Go for the pen, cross, and then do the crossing for the last one as well. Okay, so I'm left with 1, 0, 0, 2. So what I'm going to do is I'm going to have 1 times 2, that'll give me 2. And then minus 0 times 0, that'll give me a 0. So with that said, this is going to give me 2. So the last part will give me a 2. So that's it. So that's how we find a minus. But the question is, when we find a minus, what do we use a minus for? We need to now use it to find the cofactors, which is this one. So, which is this? All right. So now let's come back here. Any question on the minus before we go on to look for the cofactors? See whether any hand is up. Joshua. Joshua, I see your hand up. Okay. Joshua is not available. All right, so I think we can move on. Okay, so now with the minus, finding the cofactors is very easy. Please pay attention here. This one is Minta.
Please, the last concept, the diagram, I didn't get it. Please.
Diagram.
The last concept, finding the minor for the last one. The negative
With this one, with the 2, right?
The negative 2, starting from the negative 2.
From here.
Yes, please.
Okay, so let's look at this first. All right, because that's what I'm on now. So this positive 2, we cross like this, right? You are left with 1, 0, 0, 2. So that'll give you 1 times 2, which is 2, minus 0 times 0, which gives you this 2. Okay? Now, if you come back, clean. So now I'm going to go to the 0 here. Okay, then I'll come to a negative 2 mentioned. So with a 0, I'm going to cross like this. I'm using a different pen, don't worry. So that's now for this 0 to give us this 3. Okay, so that's going to give us 1 times 3.
It's very easy.
Minus 0 times 1, which gives me 0. And that's why we had a 3 here.
What are you doing?
Now to come to where you have your
Look at it.
negative 2, all I'm going to do is let me clean. So that this cross and this also cross. So that's now going to give me 0 times 3, which is 0, minus 2 times 1, which is 2. And that gave me my minus 2 here. Please, do you understand now?
Yes, thank you very much.
Okay. So we can move on now, right? All right, now that we understand the minus, getting the cofactors is very simple. You remember the plus minus thing we were doing back in the finding the determinants, right? So that's what we're going to apply here. So we're going to apply a plus. This is now cofactors, right? Cof of A. How do we do that? How we do it is that we pick the minus, then we introduce plus and minus to it. So let me write them here so that someone will not come and ask me a question. So 2, this would be a 3. This would be a 2. This would be a 0. This would be another 2. So I'm just repeating what we have for the minus, right? And that will help us to get the cofactors. And this should be minus 2. This should be 3. And that should be a positive 2. All right, and I'm going to use a different color altogether to explain. So maybe let me pick a purple, yeah. So for us to find the cofactors, once I have the minus obtained, it's just going to give me a plus here, a minus, a plus, always start with a plus, minus, a plus, minus, and this should be plus, okay? So let me write the plus somewhere here. Because there's already a minus there, so I'm not touching it, right? Then this guy will be a minus, and this should be a plus. That's it. So the cofactors is just multiplying each of the aij's by a plus 1 and a minus 1 systematically and respectively. So at the end, the actual cofactors, right, will now be in this form. So this will be plus 2, which is the same as 2. This will be minus 3. So I write down minus 3 there. And then this will be plus 2, which is still positive 2. So I write the 2. This guy is minus 0, which is the same as 0. This is plus 2, which is the same as positive 2. This is minus 0, which is the same as 0. This is plus of negative 2. So plus 1 times negative 2 is going to give you a negative 2. Then this is minus 3. And lastly, this is positive 2. Please watch it. Your cofactors will never be the same as a minus in terms of the signs. The elements will be the same, but the sign in front of them will never be the same. It's not always the case. So if you compare, this is 2, of course, this was 2, that's true. This is 3, but when it came to the cofactors, it became minus 3. This is 2, this becomes a 2, this is 0, 2, 0. So the second row, they are the same. And then, but when it comes to the third row, this is minus 2. Yeah, that's correct. This is 3, but this is minus 3. And this 2, that's also 2. Any question on the cofactors? Very good. So now, what is the formula saying? The formula is saying that for us to be able to find the inverse, transpose the cofactors of A. Very simple. So if you are transposing the cofactors, because this is what we have done, we have been able to get this. This is where we are. We are here. So now to be able to go ahead to get the adjoint means that we are supposed to transpose it. So transposing means that the whole of this row, first row, will become a column for the adjoint. The whole of this second row will become a second column. The whole of this third row will become a third column. That is it. Work is done. And that is what gives us this formula you are seeing here, the adjoint, this guy. But the adjoint here means cofactors transpose. COF of A, which we have found, just transpose it. Transpose the whole result you have had. And I'll give you the adjoint. So that's it. So once I'm able to get that, all I'm going to do is that I'm going to now pick 1 over the determinant of A. And what did you get for the determinant? I got 4. So I'm just going to now, after transposing it, right? Transposing it now give us the adjoint. So let me write the adjoint here. I use a different color. Let me see whether I can get a green. Let me use this color. Yeah, let me see what I can write it here. So if I'm transposing to get the adjoint, probably I'm going to get something like this. So 2 minus 3, 2 will be a column. So that's going to give me 2 minus 3. And then another 2 down here. And then now the second row will now become a second column. So that's going to give me 0, 2, and then 0. And lastly, the third row will now become a third column. So that's going to give me minus 2, minus 3, and lastly positive 2. Okay, work is done. So with this, that gives me the adjoint. Then 1 over the determinant, in other words, reciprocating the determinant, is going to be this. So the whole of that coming in will now be 1 over 4. It is very simple. So it means that this first part will be 2 over 4. That'll give me what, 0.5. This guy will be 0 over 4. That'll give me 0. This will be negative 2 over 4. That'll give me what, negative 0.5. This guy will be negative 3 over 4. This guy will be what, 1 over 2, because it's going to be 2 over 4. This guy is going to be negative 3 over 4. This guy, I think, is 2. Yeah, 2 from here. So that'll be 2 over 4. That'll be half. 0 over 4, that'll be 0. 2 over 4, that'll be half. That's it. So I'm done with the inverse for this particular example. Any question? Minta?
So I really understand, but for the concept of using 1 over 4, but the determinant was 4. And for the question 2, they didn't notify the inverse. So why did we find the inverse?
Sorry, you said the question didn't say we should find the inverse.
He said we should find the cofactor of A transpose. That is equal to the adjacent. The adjoint A.
Yeah.
So how we got the inverse is what I don't understand.
Oh, the formula for the inverse is this one. See. This is the formula for your inverse. So if you have been able to get the adjoint, then what are we having? 1 over the determinant.
So it is compulsory that the moment you get the adjoint, you inverse this.
You multiply by the 1 over the determinant, yes. Because that's what gives you the formula for your inverse. Please, do you understand?
Yeah.
Okay, sure, great. Remember, all these things calculator can do. Joshua Anand.
Yeah, thank you, sir. Please, can we refer to our senior high school segment, or if you refer to the slide?
Please come again.
I'm asking whether we can revise our senior high segment or use the slide. If you can use the
You can
senior high
refer.
school.
You can refer. I'm very sure it's the same concept there. The same thing. Okay.
Okay.
All right. The next person on the call is Patrick. Okay. Oh, time is even up, right?
All right.
Sorry, you have a class after this, right?
Yes, sir.
Oh, sorry about
Yes,
that.
sir.
I didn't even know time is up. So please, then I will have to end here. Before that, let me hear from Prince and then Patrick. Prince, let me hear from you.
Okay, thank you, sir. Please, my question, so we simply leave our answer for the inverse. We can leave it this way without having to convert the values, like by dividing them by 4 individually and writing them as a big matrix.
Yes, you can leave it like that. But you see, if it's going to
Hello.
be MCQs, your exams will be assuming MCQs. Assuming you leave your answer like this and you go and check the answer is not like that there. Then you get what I'm trying to say.
Okay, so we have to do the conversion. So it will be 2 divided by 4. Then we put the actual decimal value there.
Exactly. If it's exams, you have to check what is there.
Okay.
Do you understand me?
All right.
All right. The last person, Patrick. Okay, Patrick is not available. All right. So guys, thank you. Sorry, I have to take much of your time. I don't know what is on the comment section. Kelvin, can you hear me? Kelvin. Okay, so I think Kelvin is on the call now. So normally it is Wednesdays, and that is what I know. I will get, I think the time. Andrew, I see you on the call. Your classroom, who is your classroom? You guys have a rep?
Yes, we have a rep.
I don't know.
Okay, the rep should just send me her on WhatsApp. Okay. I'll send you the TS contacts. Then please call him. Okay, all right, I think that's it. So I think if there's nothing on the table, let me end the session. And then you can get
Sir,
ready.
please send the recorded video too.
Yes, the recording is very, very important.
I'm sorry, I'm not the one who records. I think Vida, so probably those who record, you can actually share with me the link and I'll post it on.
By please, if it is you, then you do justice.
Sure.
All right, so maybe Vida, you can get in touch. Maybe
Okay.
get me the recorded one, and then I can upload it on OneDrive and put the link on Sakai.
All right.
Everyone, right?
Sir, please, your number so I can send it to you.
Any assignment?
My number is on the course online.
Okay, sir.
What that?
So then I'll do that.
All right, say bye-bye.
Hey, who is that person? Who is that?
The one saying any assignment, please relax, relax.
Terry, you this Terry guy, no problem.
You don't mind this guy. One day we'll go beat
No
up.
problem. Me and my Georgina, we go meet you for one corner.
You last time I went and defend you on the platform, and today you came and repeat that thing again.
What assignment are you